This time, passive networks, which includes equivalent models of real passive components. For example, consider this circuit with a passive component there with a complex impedance Z. We can see that the voltage across this component is currently given by the phasor with an amplitude of 1 and a phase angle of 0, and the current flowing through that component is given by a phasor of amplitude 894.4 microamps at a phase of minus 26.6 degrees. And we've displayed the voltage and the current on this display as before. Now, what happens if you multiply these two together to get an idea of the instantaneous power associated with this passive component? And the answer is this. Now, this power is positive for almost all of the time, which indicates that for almost all of the time, this passive component is removing energy from the circuit. But just occasionally, at one point in the cycle there, the instantaneous power goes negative, which means this component is returning energy back to the circuit just for this short amount of time between the zero crossing of the voltage and the zero crossing of the current. How can we calculate how much current is being pushed back into the circuit and how much current on average is being dissipated? Well, the trick to that is to represent the complex impedance of this general component as a real part plus an imaginary part. You could always express the complex impedance of a component as a real part and an imaginary part. And the real part is going to behave like a resistance, and the imaginary part is going to behave like either a capacitance or an inductance, depending on whether it's a negative or positive imaginary component. We know that there is no power dissipated by an ideal capacitor or an ideal inductor in a circuit because the voltage and the current are 90 degrees out of phase. So all of the power that's being dissipated by this equivalent network, it will be dissipated by the real part of the complex impedance, this part here, the resistance. All we have to do is work out what that is. For example, suppose we had this passive network, two 1K resistors and a 1 millihenry inductor, and we want to know how much power is lost when 20 milliamps in total current is flowing through it at 100 kilohertz. What we need to know is what is the total complex impedance of this network expressed as a real part plus an imaginary part. And we can work that out. Z, the complex impedance of the whole network, is just going to be a 1K resistor. I'll just call it R for now, plus a 1K resistor in parallel with that inductor, which I will call L for now. So that's R times j omega L divided by R plus j omega L, standard formula for two components in parallel. Right, we'd need to express this in terms of a real part plus an imaginary part, so we'll need to express this term here in terms of its real and imaginary components. And the standard way to do that is to multiply top and bottom by the complex conjugate of the bottom. So that would give us R plus R j omega L times R minus j omega L divided by R plus j omega L times R minus j omega L. And if we multiply out those, that would give us R plus R squared j omega L minus j omega L squared times R divided by R squared plus omega squared L squared. And if I separate out the imaginary component of this, that's just going to be that term there, because this term here has a j squared in it, and j squared is minus 1. So that would give us R plus omega squared L squared R over R squared plus omega squared L squared, plus J times omega L R squared over R squared plus omega squared L squared. That is our imaginary component. This is our real component. If we know the total current flowing through our passive network, and we know that we can represent our network as an inductance and a resistance, where the resistance has this value, and the inductance has an equivalent value given by L R squared over R squared plus omega squared L squared, then I know that all of the energy being lost to the circuit is being lost in this component here. I know the current flowing through it. I know the value of the resistance. So the power being lost is the current squared times the value of the resistance divided by 2. That's just from the formula. The average power is I0 squared times R over 2, which here is going to be, well, the current is 20 milliamps, so 20 milli squared over 2 times all of this lot. And from there, it's just a case of plugging in the numbers. So let's have a go. R, my resistance, is 1K. Omega, the angular frequency, is 2 times pi times 100 kilohertz. And L, my inductance, is 1 millihenry. Our effective resistance, what I've called RF here, that's the real part of the complex impedance of our network, I'll just call it Q for now, is R plus omega squared L squared times R divided by R squared plus omega squared times L squared, or just over 1.28 K. So our average power being dissipated by this component is 0.02 squared times that effective resistance divided by 2, or just over 1/4 of a watt. In terms of the power being stored and then pushed back into the circuit by the reactive part of the total impedance, I could do a similar calculation, but I'd be looking at the imaginary part of the complex impedance there and determine what that told me about the maximum energy being stored. When the rate at which the energy is being pushed back into the circuit is greater than the rate at which the energy is being dissipated by the resistive component of the complex impedance, that is the part of the cycle where the total component has a negative power associated with it. The energy being returned from either storage in the electric field or magnetic fields in the capacitor and the inductor is more than enough to allow the energy to be dissipated by the resistive component, and the excess energy is returned to the rest of the circuit. Next time, we're going to have a look at how both of these types of power, the power that's actually physically being dissipated in heat and lost to the circuit, and the power that is being alternately stored and then released back into the circuit from the electric and magnetic fields in reactive components, can be combined together to produce a convenient quantity called the complex power.